All right, looks like I had a little bit of a hiccup there. I'm sending out a new stream link to everyone. It's the same link, just letting everyone know I redid it. Went back and edited it in the studio, and it looked like I only lost about 15 seconds. Um, so I'm going to do the second function I was going to do. Um, I have no clue what happened there. Um, as I saw you type that, like I said, only about 30 seconds, which isn't a bad reaction time, but sorry for what happened in the middle. I'm just getting an email out to everyone while I get started here. So I had done the composition of I had done both compositions of x plus 2 for f of x, and g of x was x cubed minus 2x squared minus 1. I didn't fully, you lost the multiplying the x plus 2 cubed out, which is okay. The book doesn't even do it. It leaves it in its x plus 2 cubed form. But what I want to do is I want to focus on some domain restrictions and how they propagate through to the final thing. Um, and yeah, and some things we can tell. So I'm gonna look at I'm gonna look at both of these here. Sorry, trying to get my blackboard to be black. I don't know. I find I work on screens a lot now, and I used to work on screens a lot before. That I don't like the bright white screen because it's a lot of light. So I like things that are black screens with the light coming through. It's easier on my eyes. I know the white feels more papery, but when I'm looking at a screen for 3 or 4 hours a day, a lot of white back screen is a lot of light coming through. If you ever look at how the screens operate, there's a light behind it, and then the pixels open and close, letting the light come through. So a white page is a lot of light hitting your eyes. And when I used to work for IBM, and I just looked at screens for ages, I found different color settings were easier on my eyes. Which is why you see me using these blackboards. And the guy from Khan Academy, Sal, I honestly thought his approach to that and what he set up to use for that was the best for the visual media. I've seen a lot of people use whiteboards, and I just can't look at them for long periods of time. Well, I can. It really depends on the presentation they have. I will get over my distaste of it. So let's look at a couple functions here. All right, so I'm going to look at a function that has definite domain restrictions. We're going to have the square root of 2x and we're going to have 1 over x squared minus 1. Now, the thing I want to keep in mind when I will be composing one function of another function, when I'll be doing anything like this, is I want to look at my domains. And because this isn't a square root, what's inside the square root has to be greater than or equal to 0, or x has to be greater than or equal to 0. So my domain of f x has to be greater than or equal to 0. Now my range of f will only spit out positive numbers also, right? We don't get negative answers to square roots. I can't take the square root of something and get a negative value. It ain't going to happen. They don't do that. And I want to keep this in mind because domains and ranges are getting exchanged here. So we want to kind of have an idea of what the domain and range is of all the functions we're using. All right, so my domain of g, well, I cannot divide by 0, right? And so x squared minus 1 can't equal 0. So x squared can't equal 1, or x can't equal positive 1 or negative 1. So I'll put my new domain in here. x can equal 1 or negative 1. I'll write it like that because I'm running out of room. Now its range might be a little bit harder to see. Well, I have a positive value with no variable up in the numerator. So there is no way this is ever going to equal 0. If these are really, really small numbers, I will get negative numbers, but the smallest this can be is 0. All right. So x has to be greater than negative 1. Negative 1, right? X is greater than negative 1, but it can't equal 0 on its range. So it would spit out a negative 1 here. Would it make anything less? I don't know, but as it gets bigger and bigger and bigger, these can get smaller. So this has the ability to do all real numbers. But it can't equal 0. Well, let's double check that in the graph. Right, so we're using what happens if I'm doing a division and I divide by really small numbers, g is going to get really, really big. And if I divide by really big numbers, and I should have the ability to do both, I should be able to have g take on all values. And it does have the ability to get some negative values. Where are you guys here? So let's look at the graph of this. So I'll come over here. I'll just change these around for us here. This was square root of 2x. And this is going to be x squared minus 1. And there's our asymptotes at positive 1 and negative 1. Definitely shoots down to negative infinity in the middle. Shoots up to positive infinity. So it can be all real numbers except 0, or horizontal asymptote for g of x. And f of x has to start at 0 and head off towards positive infinity, but it has no negative numbers. All right, that's not too bad. Let's look at what happens when we compose these things together of each other. And compositions might feel weird. They have a definite real-world application that's very, very useful. They're also going to help us move through the next couple of things we do. So we should keep looking at this. All right, let's pull through here, switch over to the blackboard. All right, so we have our idea of our domains and ranges of these functions. So let's look what happens when I take f and I compose it of g. So f composed of g. So I'm going to have the square root of 2 times 1 over x squared minus 1, which is equal to the square root of 2 over x squared minus 1. And that's our new function. That's about as simple as we're going to get it, but we can say some things about this. So my f and g. So g gives me the domain restriction that I cannot have 0. 0 is not going to be applicable in here. So my domain of my composition, x is going to be all real numbers, but it can't be 0. Because it inherits that, or I'm sorry, it can't be 1, negative 1. But it can still be 0. Because the domain of g, I was saying it backwards, the domain of g is driving this. If I spill 0 into this, my range becomes the input for f. Well, this is never spitting out a 0. So it satisfies this here. And now I need values that are greater than 0. So x can't be 1 or negative 1. And x actually has to be greater than 1 or less than negative 1. What do I mean by that? Well, with what's inside of here can't be less than 0, I get a negative number when x squared is less than 1, right? If x squared equals 0.5, 0.5 minus 1 is negative 0.5. So if this thing here has to spill into this restriction. So we get the added restriction. The math I'm doing in my head here, I'll do it out. X squared minus 1 has to be greater than or equal to 0. Because we can't get negative signs. No negatives. So x squared has to be greater than equal to 1, or x is greater than 1, or less than or equal to negative 1 for that to work. And so that how that comes through. But it can't equal 1 or negative 1 because the original restriction. So this goes away. So notice domain restrictions, we have to look at what's happening to our function. We have to look at what's happening to our function's range. And the rule that generates this number here, generates this, spills back over here. And so I have an acceptable set of values from 1 to negative 1. So let's look at f of g. Let's look at what this ends up looking like for us. Turn off the other ones. And so notice we lost the middle between those two values. It spits away. That's what we mean by this. That the combination of these two rules, this middle section here, doesn't satisfy the composition. Any of the values in here were negative, and negative values can't go in to a square root. They'll give us imaginary answers. And so the values between 1 and negative 1 won't fall into our new composition. And we see that in the composition. We lose the middle values. And that's what I mean by the rules spilling into each other. I would use your graphing software as a key for that, so that you can have your graphing software kind of help you see these gaps and these restrictions as they come through. All right. We'll do some examples of these, but I want to introduce one more thing, which is section 2's idea, which relates back to the compositions. And it's going to be the idea of the inverse. And so I'm going to end with the idea of the inverse, and we'll do a lot more examples on Tuesday when we come back into this coming through. But we have our idea now that I can combine functions with operations, and whatever domain restrictions I have of both functions come into the new function with operations. When I make a composition of a function, the domain restrictions, the domain and range restrictions propagate through with how the rules interact. And so I find that keeping track of domain restrictions with compositions of functions takes time. You sit down, you list your domain and range of the one function, the domain and range of the other function, you make your composition, and you look at the range going into the new rule. You look at the range going into the new rule, and you carry over your initial restrictions, which is what we did here, right? G excluded these two values. When I applied the output, I had to reapply this restriction. This whatever is under the square root has to be greater than or equal to 0 in terms of this couldn't end up being negative. Right? And that's that extra step that we have here now, is the range of the one gets applied by the rule. So it does take a little bit to find out what gets limited. And in this case, it said, hey, nothing in here is going to work because whatever is spitting out of 1 over x squared is negative here, and that's not going to work under the square root. So I had a big frowny face, right? Those were my negative things, where the other sides were doing this. And the square root just wasn't going to take those. But it would take the rest of these because they're spitting out positive values. It's weird how two simple rules get really complex, right? Because the rules we have for restrictions right now are that square roots, what's inside of them, even power roots, what's inside of them has to be greater than or equal to 0. And we can't divide by 0. Those are the only two rules. And yet, as our functions manipulate our values through many things, those rules get convoluted and twisted and turned. And we get weird shapes. Where we're saying, hey, we're not taking these because they're less than 0. All right, let's look at inverse. Inversion is what mathematics likes to do. If I add something, I want to be able to go backwards, and I invert it by subtracting. If I multiply something, I want to be able to go backwards, and so I reverse it by division. Now, these things for us were inverses of each other. So we had A plus B equals C. We could turn that to C minus B equals A. We could reverse the process. And we also had rules to create inverses where A minus B is the same as adding its inverse. Well, A times B equals C, so C divided by B equals A. Or we had the idea that A divided by B was equal to A times its to B's reciprocal. These are kind of the concepts of inversion. And we had, if I do exponents, we had roots. Okay, these are the things in PEMDAS. And so x squared equals B, then the square root of B equals x. We can invert powers. Now, sometimes we got restrictions with the powers. We can't divide by 0. There are things that happen that limit everything we can do with inverses. And those limits are actually domain and range restrictions. We can think of these as functions. But in general, if I have a function, again, I'll use my domain mappings, working in domain D, and it generates a range E. And so this is F. And F's job is to take any element in D and map it to an element in E. And so we're going to take a specific elements here. So we'll take element A, and this ends up on element B. I'll finish my lines here. All right, this goes all the way in here, and that'll make element D. And that'll be element F. And so for each element, F maps to another element. Well, if we want to map back, let me use obnoxious purple to map back. We're going to call that an inverse. And an inverse gets this -1 up above. It's a reverse mapping is an inverse. We undo the work we just did in the function. We go backwards. And so an inverse is a way of mapping back or undoing the operation. And so we undo our conversions. And so inversing can say you take your steps and you do them backwards. So let's look at how an inverse will work and what this is saying in a representation. I want to find a good one here and show you the technique for making an inverse. And so what I'm going to do is I'm going to use our normal variables. We would say these are the x values, and these end up being the y values. So if I want to invert a function, I replace the function f of x with y. I switch x and y. I solve for y. I call this my inverse. So we're going to use a variable trick to write this in a form that's easy for us, and we reverse our mapping. We change our rules backwards. So let's look at a few of these here. So I'm going to invert in sky blue. So I have f of x is equal to 2x minus 7. So this is a mapping. I put in something in my domain. This rule spits out something in my range. But if I want to start with my range and go backwards, right? And we do this all the time. We do conversions in one direction and we do conversions in the other direction, right? You want to know what the temperature is in Celsius. You have your formulae to calculate Celsius given Fahrenheit. You want to go the other way. You have your temperature in Fahrenheit or in Celsius, and you want to know Fahrenheit. You have your conversion that gives Fahrenheit equal in terms of Celsius. And so conversions are bidirectional functions where we can take inverses of the functions. Well, let's follow these rules here. Let's use these rules to help us. So I'm going to replace f of x with y. But this is my range and this is my domain. I want to go backwards, so I want this to be my domain and that to be my range. Right? I switched x and y. And now I'm going to solve for y. And the process of solving for y reverses all the rules the function does. So I'm going to add 7 to both sides. Divide by 2. And I'm going to say this is my inverse. The inverse of the f function is equal to x plus 7 over 2. So this becomes our process for taking inverses. Let's make some inverses. And we'll keep coming back to this rule here. So I'm going to replace f of x with y. I'm going to switch x and y, and I solve for y, and I call this my inverse. That was that one. Let's go to ugly yellow. So ugly yellow, let's do one. I want to involve a root here. I have like 6 listed on my sheet here, and I want to do one that, actually, I'll do this. So these ones are a little bit harder, but some things can be learned from them. All right, now I know I have something in the denominator here, so I have to worry about domain restrictions. And so I'm just really quickly in my original function, x cannot equal 1. For my domain. All right, so let's take our rule here. I write this with a y. Y equals 2x plus 1 over x minus 1. That was my step 1. Step 2, I swap x and y. So x equals 2y plus 1 over y minus 1. And now I'm going to solve for y. Well, I want to cross multiply here. So I'm going to get x times y minus 1 equals 2y plus 1. I'm going to distribute. Xy minus x equals 2y plus 1. Now I'm solving for y. So I'm going to bring this up here. I'm solving for y, so I want to gather my terms with y together. So I'm going to subtract my 2y from that side, right? Subtract this over to here, and I'm going to bring the x over to here. Now, both of these have a factor of y, so I can pull the y out front. And I'll divide both sides by x minus 2. Make sure, let's see. Cross multiplied, checking my signs here. Yep. And I'm now going to call this my inverse function of f. Notice my inverse, the inverse has a domain restriction that x cannot equal 2. Which kind of suggests that in the original function 2 wasn't popping out. And if we look at this first function, and we look at our rules of rational function, this does have a horizontal asymptote at 2. And so, yeah, this could not be 2. Notice how those asymptotes keep popping back up. So inverting a function undoes all the rules of the function, and we're going from our range to our domain, our range to our domain. Let's look at this graphically, and let's look at this one and its inverse. So clear these out of here. Get you over to the graph. Alright, so for right now, I'm going to put in a very special line, y equals x, because I want it there. And then let's see, in my first function here, I want 2x minus 7. Oops. And for my second function, the inverse of that was x plus 7 over 2. X plus 7 divided by 2. Notice something that happens with these lines. When an inverse takes the domain of one function and turns it into a range, so it's taking all the x values for this green function and saying those are now your y values. And it's taking all the y values for this green function and saying they're now your x function. Well, that mirrors this across this line here, our line of y equals x. So inverse functions mirror across the line y equals x. See that mirroring effect going through? These things mirror, they're equal distance off of it. So an inverse function graphically, and this is really, really important, graphically mirrors the function across the line y equals x. By taking the domain of one function and turning it into the range, we're flipping the x and y values. And flipping the x and y values mirror over the line y equals x. Well, let's look at a function that has an inverse that we know of. And then I said, hey, x squared is a function. Right? There's x squared as a function. So the square root of x was another function. It was the inverse. Notice it mirrors across the line y equals x. We get this mirroring effect going on. But also notice it doesn't have the negative side of this. And that's because square roots can only return positive values. And to get the other side, we need to specifically state we want the negative values by putting the negative sign in front and completing the mirror. So not all functions map their inverses perfectly. But we could talk about this having a domain restriction. Where I say I want only the positive values of x. So something is happening with our functions. When we switch these domains and ranges, they switch across this space, this graphical space that we made for them. And switching x and y mirrors across the line y equals x. I hope you can see the poetry in that. That making an inverse mirrors across y equals x, which is the base rule we use when we make our inverses. Well, to make functions that work for us really well with inverses, we're going to make a special type of function. We're going to restrict, remember, functions have to pass the vertical line test. Well, that means its inverse has to pass a horizontal line test, which x squared doesn't do. And so we're going to make a special set of functions called one-to-one functions. And first I'll define what isn't a one-to-one function. And I'll look at x squared as an example. X squared, if I have the element -1 and +1, mapping over to its answer, right? So this is the function x squared, and I guess these are all the original x values. +1 maps to +1, and so does -1. Two lines end up on one place. Now for a function, that's okay to move in that direction, but you can't go in the other direction. If I'm at 1 and I need to go backwards, I don't know which line to take. And so this is not one-to-one. All right, this is a 2-to-1. All right, these two values cascade into one value. So we can make it 1-to-1 if I say, hey, I want x to be greater than 0. I lose all the negative values, and I have the one line. Well, this lets me write a specific type of functions that are invertible. And so let's define it in the book form. So a one-to-one function is a function f is 1-to-1 if elements c and d in the domain of f do not equal, and f of c does not equal f of d. Which means that a different input always has a different output. Most of our functions that aren't one-to-one, we can make inverses, or we can make them one-to-one by restricting their domain. And so every one-to-one function has an inverse. So x squared is not one-to-one. And so it doesn't have an inverse. But if we restrict its domain, if we say x is greater than 0, and we restrict that function, we've now made it one-to-one. And that's the thing we do with the square root sign all the time. We say we're only going to get positive answers from a square root. Well, what that's saying is we're only taking the positive values that we squared. Well, inverses have a really nice feature, and that's the test for inverses. If I take f and I compose it of its inverse, I'll get back just x. And, there's an and here, if I take the inverse and I compose it of f, I also get back. So let's look at the one we did earlier, the, what was it, 2x minus 7? And its inverse. Let me see if I can find that one. And we'll check to see if it's one-to-one. I know it's one-to-one. I just want to show you the test for it. Actually, I'll use an even smaller one. We'll say f of x. Is it 2x minus 7? I thought it was 2x minus 7. Had it right here and I lost it. Well, we'll do 2x minus 7. So we'll find the inverse. We'll say y equals 2x minus 7. We'll change this to x and y. Oops, 2y minus 7. I'll add, yeah, that's the one we did before. And so my inverse of this is x plus 7 over 2. Right, that was the one I had. I just had to work out what the answer was really quick. So we're saying these two things are inverses of each other. Well, there is a test we can do for this. And that test is going to be, I'm going to compose f of its inverse. So let's do that. F composed of its inverse. So f composed of its inverse, so this is going to fall in for its x value. Now let's simplify. The 2's cancel, and I get x plus 7 minus 7. Well, that does equal x. So it passes this check. Right? If I take my f function here, and I drop into it its inverse, those cancel, I get x plus 7, the 7's cancel, I get x. In other words, if I put in x, I get x back for the composition. And since the domain of an inverse is the range of the function, these should be cyclical for this. This test should work for us. So I'm going to take my inverse and I'm going to compose it of my original function. So my inverse is x plus 7. Now wherever I see x, I'm going to plug in my original function. So I'm going to get 2x minus 7 plus 7 over 2. So the 7's cancel, leaving me 2x over 2, or x. So I pass this test. So inverses are things that if we compose a function of its inverse, we get x back. Just x, nothing else. And if I compose the inverse of its original function, I get x back and nothing else. And that's how we test to make sure an inverse works. All right, I'm going to leave it at inverses here. Homework is up. Your exams are up. If you need anything, please, 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 please email me. Be safe, be well, all right? Sorry about the cutout earlier. That stuck on that graph, did it? Okay. All right, I'll fix that. I'll edit that down. Thank you.